Okay, hello everyone. So we're now on the next module, which is chemical equation. So this is a follow-up of your writing chemical formulas module. So if you watched that, thank you so much. And this will be the follow-up module for that. So let's start. So when you talk about chemical equations, first we have to understand the anatomy of a chemical reaction. So usually in this figure, reactants always appear on the left side of the equation. And of course, products are on the right side. So, of course, just like any equation, there's an input, there's an output. So again, on the left side of the equation, that will be your reactant, and on the right side would be your product. You can also see notations like this one. So you can see here you see something like a G, 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 maybe perhaps in other materials you've seen L or you've seen S. So these are states of matter. So when it's G, it means this is gas. S is for solid. L is for liquid. So it says here the states of the reactants and products are written in parentheses to the right of each of the compound. So if you really want to create or write a chemical reaction properly, then you have to include everything, including the states. So in this case, that's gas, 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 and let's see, this is probably also gas. Okay, so let's go to the next one. So this was already discussed in the last module, but let's have a review. What about subscripts and coefficients? So they actually give you a lot of information about the chemical reaction or the chemical equation. Your subscripts are uh, representations of the numbers of atoms of each element in the molecule. These are the small numbers, subscripts. They tell you how many atoms are there in that compound. Okay, how many atoms of a specific element are in the compound. Whereas coefficients are different, they tell you the number of molecules per compound. Say here, for example, here, let's check here, H2O, that's of course water. You know that there's only one molecule of water. However, in that one molecule, there are two hydrogen atoms and one oxygen atom. This is two molecules of water. In two molecules of water, it means that you have four hydrogen atoms and two oxygen atoms. For hydrogen peroxide, for one molecule or one molecule of hydrogen peroxide, you have two hydrogen atoms and two oxygen atoms. Okay, let's have a longer one. Let's all consider this chemical equation. So let's check for the first part how many of each element we have. So this is 4 moles, 5 moles of oxygen, 6 moles of water, and 4 moles of this. Okay, but how many of each atom are there per molecule? So in this case, there are 4 nitrogen, and again, the rules a while ago, which was discussed. So this is 12 hydrogen. And then how many oxygen? We have 10. We have 12 hydrogen, 6 oxygen, and 4 nitrogen, 4 oxygen. Okay, just remember the subscript indicates indicative of the number of atoms of that same element, and the coefficient would indicate how many moles, how many molecules of that compound there is in that equation. Okay, types of course, before, for example, you really want to understand this and really go into more readings, there are actually different types of reaction. This one is a combination reaction, wherein two or more substances react to form one product. This is more or less summative, additive. So nothing is broken down. Instead, it's combining. So this is a combination reaction. These are samples. You also have one, which is the opposite, which is called the decomposition reaction, wherein one substance breaks down into two or more substances. Like in this case, calcium carbonate is broken down to calcium oxide and carbon dioxide, potassium chlorate. So this is two potassium chloride and oxygen. This is sodium nitrate, so sodium nitride. So we have two sodium and three nitrogen. And the last one is a combustion reaction or combustible reaction. These are rapid reactions that have oxygen as a reactant. Sometimes they produce flame. Always remember that when it's combustible, there's always the presence of oxygen. So most often involve hydrocarbons reacting with oxygen in the air to produce carbon dioxide in water. So these are examples. You can see that for every part there is oxygen. Okay, okay, let's go to the next one. What about different numerical values that we will be encountering? We have the first one, the AMU unit or the atomic mass unit. This is defined since 1961 and it is actually 1 over 12 mass of the carbon 12 isotope. So there you go. The reference is especially in carbon dating, it's the carbon isotope. So the AMU unit is defined as this one, uh, 12 AMU for one carbon isotope. Okay. Then for other formula weights, what is a formula weight or what are formula weights? This is the sum of the atomic weights for the atoms in a chemical formula. You know, from your periodic table, you actually have atomic weights or yeah, atomic mass or atomic weights. That's how we call them. So the formula weight of calcium chloride, for example, CaCl2, would be, you just refer to your periodic table. Let me just, let's see if I can pull that up. Let's go back to our periodic table. Oops, sorry. I think I opened, oops, it's not. I'm sorry. I think I opened a different, okay. Let's just check for carbon. You know that carbon is usually, oops, okay, let me just open that again. You know that, okay, I'm sorry, calcium has 40 atomic mass, and then chlorine has 35.5 atomic mass, and all you have to do is multiply the subscript to that atomic mass and then put them together or add them. So since we only have one calcium atom here, 1 times 40.1 and chlorine has 2 times 35.5 and it means that the whole compound has 111.1 atomic mass unit. Sometimes it's interchangeable that they use grams instead of uh, AMU or grams per mole. It means for every mole of that compound, how many grams are there. So, but these formula weights are usually used for ionic compounds. There's another one which is molecular weight, which is interchangeable, some of the atomic weights of the atom in a molecule. For the molecule ethane, for example, C2H6, the molecular weight would be, of course, how many carbon atoms do you have and how many hydrogen atoms do you have? You have 6 and 2, so you just multiply it by the atomic mass unit or the atomic weight. So that's 2 times 12, 6 times 1, the whole thing is 30 for ethane. For percent composition, if you just want to really get the percentage of the mass of a certain compound in the whole reaction, you can use this formula. Number of atoms or percent of the element is equal to the number of atoms times atomic weight all over the formula weight of the compound times 100. Of course, later on, there will be examples for this wherein I'll be solving one equation and using different scenarios to be able to get the different numerical variables that we need. Okay, for example, for ethane, uh, what is the percentage of carbon and hydrogen in ethane? So we can just get the whole atomic mass unit of ethane, which is, of course, we solved a while ago, which is 30. And then there are two atoms of carbon, and then times the atomic mass unit, that's 24. And then likewise, do the same thing for hydrogen. There are 6 hydrogen atoms, and this is 30 for the whole ethane. And just do the math. Eventually, you get 80% of carbon in ethane and 20% hydrogen in ethane from the numerical computations. Okay, what about the mole? The mole has a lot of technical definition, as you can see. By definition, the carbon is equal to 12 AMU, 1 AMU is 1.6605 times 10 to the negative 24 grams. We won't be doing or using much of Avogadro's number for our solutions because it's only limited up to stoichiometry. But I will have a different, another presentation specifically for this, problem solving regarding Avogadro's number, the mole, etc. For now, I'm just introducing to you the different terms that we'll be using eventually. And the mole, in layman's terms, is just a number of things. You say 1 dozen is 12 things, a pair is 2 things. This is just comparatively stating it. There you can say that 1 mole is like 6.022141 times 10 to the 23 things. If you assume it's just things, okay? In layman's terms, for you to understand it, okay? Because there you go, 6.02 times 10 to the 23rd, weigh 12 grams because that is 1 AMU. So let's go to, I'll be skipping some of this because I have a separate presentation. So that's it for this module. So the last one is all about stoichiometry where we'll be doing problem solving. So stay tuned for that video. I'll be uh, doing another one and publishing it in a bit. Okay, so stay and please watch the next video. Thank you.